All right, so all of that commentary and plotting for overthrowing the world with Rick Roll is not recorded, so no one will know. I'm testing primarily with the sample main program from the assignment. So as long as you ran your indexer with that main program and it produced the same output, you should be totally good to go. So that should be fine. Awesome. You're welcome. So any general reflections or thoughts on PA2? This whole process of using objects and working with classes and so on. Is it making more sense now? Yeah. Yeah, you can set index to null to start. I think it actually begins life as null. Or you can, declare, hash map index equals null. Or you could set it to null in the constructor, and so on. All right. Well, I will get those graded this weekend. I'll get going on that tomorrow probably, and I'll give you feedback if there's any issues I see. But same comment that I make every time with these assignments, right? This is a really good exercise for preparing us for what's coming next. PA3 is kind of a step in a different direction, where we're back to making our own classes kind of from the ground up. But then PA4, we're totally going to be doing things like we did in 2, where we're really using pre-existing classes, in this case classes that are used for making graphical objects on the screen, and using those to do other things. And then PA5 will take the classes that we built in PA4 and some built-in classes, and we'll add networking to whatever game we develop in PA4. So we're going to be doing a lot of what we did in this previous assignment going forward, which is really digging into classes and just using them as building blocks to make bigger things. So if you're not quite sure what was going on in PA2, even if you get a good grade on it, if you're not feeling pretty solid about it, definitely ask questions, come by office, and we can go over your code, whatever is going to help to make sure that you feel pretty good about this when all is said and done. And that'll leave you in good shape for PAs 4 and 5. Alright. I don't know why my Zoom only lets me look at 4 things at a time. Anyway, that's Zoom. Alright, so any other comments, questions, reflections on PA2? Otherwise, we are going on to PA3. All right, on we go, PA3. So next programming assignment is basically implementing the game 20 questions. So how many people have played 20 questions? That was one question. Including the electronic version. Right, so basic setup is somebody thinks of something. It can be anything that you specify the bounds on. It could be an animal, or it could be anything at all. And then the other person gets to ask yes/no questions. And you can only ask questions where the answer is yes or no, and you try to guess what the person's thinking about. And at first it sounds like a fairly impossible task, because think of anything. There's a lot of things you can think of. Even think of an animal. Well, there's a lot of animals, right? But it turns out if you know how to play this, you can usually do a pretty good job of figuring this out in 20 questions. And so yeah, there's these little handheld games you can get. I used to have one from Toys R Us. It's about this big and had a little LCD display on the front. And you'd hit the start button and it would say, you know, think of something, and you would think of something, and it would start asking you yes no questions, and you hit a button for yes, different button for no. And most of the time it would figure out what you were thinking of. And it was kind of freaky how good it was. And you'd think of really obscure stuff, and it would still figure it out. All right, so we're going to code this up in Java, and the assignment is posted. The assignment does not really tell you how to do this. It really describes sort of the goals and the overall structure. So let's oh yeah, Walmart has one. Cool. So let's dig into this. So let me show you some sample executions of this, and then we'll look at how this actually plays out. Well, let me do a little bit of the theory first. So this is basically just based on what's called a decision tree. So decision trees are binary trees, and they're complete trees. Every node has a left and a right child unless you're a leaf node, and then you have no children. And they're not BSTs. There's no sort of greater than, less than relationship. But the basic setup is your root node is a question, and the children, we can call these yes and no. And for us, we're always putting yes on the left and no on the right. If you switch that around, your code won't work with the databases that I'm making available. So we have a question, and we're going to ask the person this question. So let's say we want to figure out what the person's thinking of. So our first question would be, is it alive? So we'll ask the person, is it alive? If they say yes, we're going to say, okay, I think I know what you're thinking of. You're thinking of a cat. And if they say no, it's not alive, we're going to say, okay, I think I know what you're thinking of. You're thinking of a rock. All right, so playing this game, once we have this decision tree, is very straightforward. Start at the root. If it's a question, ask the person the question. Hey, whatever you're thinking of, is it alive? If the person says yes, move to the left. If the person says no, move to the right. If there's a question here, ask that question. This is an answer. And then based on their answer, move to the left or the right. And keep going until you get to a node that's an answer. And then you say, okay, I know what you're thinking of. You're thinking of a cat. Now, this tree is not going to do a very good job unless you happen to be thinking of a cat or a rock. This is not going to successfully guess what you're thinking of. But here's what we're going to do. We're going to say, okay, so who wants to be the guinea pig here? First person to volunteer. Okay, so I want you to think of something. Don't tell us what it is. All right, you got something in mind? All right, is it alive? No, okay. I know what you're thinking of. You're thinking of a rock, aren't you? Did I guess it right? Oh man, okay. All right, so I'm going to make a little tiny subtree. I'm going to put my incorrect guess over here. So now tell us what you were thinking of. A cup. All right, and now you ask the person you're playing, hey, give me a question for which the answer is yes for a cup and no for a rock. So some question where for a cup the answer would be yes, and a rock it would be no. Can you drink out of it? Okay, so these are answers. Here's a question. Can you drink from it? All right, I'm going to back up to the last question that I asked, which was, is it alive? And the person said no, and I'm going to change this node from my answer to this new question. All right, so I've grown my tree. The left branch is still the same, but the right branch is going to say no. And instead of saying you're thinking of a rock, I'm going to ask, can you drink from it? And if the answer is yes, I'll say a cup. If no, I'll say a rock. You could drink from a cup-shaped rock. This is true. Kind of like everything. I'm not going to go there. All right, cool. So somebody else who wants to try next. All right, I need a volunteer. All right, cool. All right, so think of an object. Is it alive? No. Okay, can you drink from it? No. Okay, I'm almost absolutely certain you're thinking of a rock. Am I right? No. Okay, so what were you thinking of? A car. All right, so I'm going to make a new tree. I'm going to put an answer for car on the left. That's the correct answer. I'm going to put the answer rock, which was incorrect, on the right. And then I'm going to ask you for a question where the answer is yes for a car and no for a rock. Can you drive it? All right, so there's a new question. And my last incorrect answer, which was rock, I'm going to replace that with this new question node. All right, and our tree is going to do a better job now. So, excellent SpongeBob reference. Good job. So you know, we can differentiate now between a cat, a cup, a car, and a rock. All right. So, what does this do overall, right? We start off with a root node. And if this is, you know, a nice fluffy tree, at this point we have 8 leaf nodes, right? These are 8 different answers that we could offer as what the person is thinking of. And how many questions does it take to get there? It's going to be 1, 2, 3 questions. So if we only ask 1 question, there's 2 possible answers. If we ask 2 questions, there's 4. If we ask 3, there's 8. If we ask n questions, how many possible answers could we differentiate between? Right, 2 to the n. So yeah, with 20 questions, how big is 2 to the 20th? Ballpark number. It's the square of 2 to the 10th. A lot. At least 4. So 2 to the 10th is about 1,000. 2 to the 20th is 1,000 squared. It's about 1,000,000. 2 to the 30th is 1,000,000,000. 40th is 1,000,000,000,000. So it goes up by 1,000x for every 10 in the exponent. So 1,000,000 nodes. 20 questions, you can differentiate between 1,000,000 different things, right? Which is pretty impressive. This is a really good introduction to the concept of exponential growth. Because we can go, you know, one of 1,000,000 different pathways through this tree based on the yes-no answers to lead us to any one of 1,000,000 leaf nodes. Yeah, that's a really good question. Our AI is really just a series of if statements. Well, for that matter, are we just a series of if statements? If you have enough horsepower, you can make some things look very impressive. All right, so this is how those little toys work, right? They just have a database of information inside stored probably as a decision tree. And to play the game, you start at the root, ask a question, and move left if they said yes, ask that question, move right if they said no. Keep going until you get to a leaf node. Good algorithm. All right, so let's see what this looks like. So let's play this. So let me show you my database file. All right. My current file is one question and two answers. Is it an animal? Yes, it's a pig. No, it's a rock. I changed from a cat to a pig apparently. So let's play this game. All right, think of an object and I'll try to guess what you're thinking of. All right. Somebody volunteer. Who wants to think of an object now? All right, go for it. You got something in mind? Is it an animal? Yes. All right, is it a pig? Aw. All right, what were you thinking of? A fish. So what is a question, yes, no question, for which yes means fish and no means a pig? Can it breathe underwater? All right, so let's play again. Is it an animal? Yes. Can it breathe underwater? Yes. Is it a fish? Yes. Is it an animal? Yes. Can it breathe underwater? No. Is it a pig? Yes. So now if your world only consists of pigs and fish and rocks, this thing works 100% of the time. All right. Is it an animal? Yes. Can it breathe underwater? No. Is it a pig? No. What were you thinking of? A cat. Question for which yes means cat, no means a pig. Does it meow? All right. Now, if we look at our 20Q file, it's bigger now. It's got different questions in it, and it's got possible answers for fish, cat, pig, and rock. Yeah, the 4 fundamental elements, exactly. All right. So that's PA3. It will start with a database, play the game with you, and if it doesn't guess correctly, it will ask for help, and it will update the database so that hopefully it does a better job next time. So let's play this one more time with the big database. So I need one more volunteer. All right. So you can only think of an animal for this database. So think of an animal, and then first question is, can it fly? No. Is it a very small animal? Yes. Does it live in trees? No. Is it a type of dog? A flying dog? No. Does it build dams? No. That's a problem. A lot of this is subjective, right? So this is a crowdsourced database, and so there's noise in here, and sometimes it'll go way off the trail, but it usually does a pretty good job. Okay, does it build dams? No. Does it have a long tail? No. Does it eat dirt? No. Is it a native Australian animal? It's not a Matthew. Sure. We'll take that as a yes. Does it live in water? Yes. Is it a mammal that lays eggs? That'd be great if it was a fish. I don't know if hermit crabs lay eggs. I'm guessing they do, yes. I didn't see that answer. Does it have waterproof feathers and webbed feet? No. Is it a type of turtle? Or a turtle, if you like. No. Does it have black on it? Interesting. Does it have claws? Yes. Is it a crab? Yes. Woo! All right. Java takes over the world. Yes. All right. So this is a big database. It's about 40,000 lines. And it's got a lot of stuff in here. And like I say, there's noise in here. There may be multiple pathways to an answer. There may be things that are outright wrong in here. Does it change form 5 times? Nice. Oh, an Eevee. Nice. I don't know if it asked about a mammal. Can it fly? Small animal. Lives in trees. Type of dog. Oh, okay. So that probably should have been a no. But hey, you know, it got around the noise and found the answer anyway. So I've never graphed out what this tree looks like from this particular database, but there are probably, you know, multiple nodes, multiple leaf nodes that say the answer is a crab, with different paths leading there. And if somebody somewhere along the way, you know, followed this and said it was a crab, then that becomes part of the database. So so that's a fun data set to play with. So that and the initial small database are both on the server under the temp area. All right, so let's dig into the details. So PA3. All right, you got 2 weeks for this. All right, it's due in May. It's not, you know, twice as hard as the 1 week assignments, but it's got a few parts and pieces to it, and I wanted to give you a bit of a breather also. So you got longer on this one. So you're coding up 20 questions. We're not limiting people to 20 questions. Depending on your database, it could go longer, but it's pretty hard to make a good database with, you know, 30 questions. That would be a billion leaf nodes. So submission, make a subdirectory under your repo called PA3. Make sure your main class is called PA3. If I can compile it by just saying javac PA3, you're good to go. If it's anything other, put a makefile in that PA3 directory so that I can say make and build your executable program. Let's see. See if I'm missing. All right. So high-level details. This document does not go into everything that we're going to talk about. Okay, this is basically a 3-pager that just sort of gives you the high-level structure. We're going to talk about the implementation of this in class. So a lot of this is going to come in lecture and lecture notes. You won't find all the gory stuff in here. This is just high level. So basically, you're going to implement a binary tree. Each node is going to have a data element, which is either a question or an answer, and I recommend keeping track of which it is by setting a flag. And then it's going to have 2 children, which we're going to call yes and no. And they're either both present or both missing. If it's a question, it'll have 2 children. If it's an answer, it will have no children. And to play the game, we start from the root, we ask the question, we move left or right, we keep going until we get to a leaf node. That's the answer that we propose. You mentioned this was a different type of tree because it is absolute yes, no versus the less than greater. So it's not a binary search tree in the sense that a BST, we have some sort of ordering on the nodes, and everything to one side of a node is you know, say greater than the node, and everything to the other side is less than, or vice versa. And that structure doesn't apply here. So it's just a different kind of binary tree, just not a BST. Yeah, so ordinality. That's my definition. There's probably other definitions. So you're going to implement a binary tree class, which means you're going to implement a node class, right? And it's going to be able to store that type of information. To play the game, so you're going to make a method called play that you use as part of the tree class, and it, you know, starts at the root, moves down, asks questions, navigates to a leaf node. When it gets to the leaf, it should ask the user if the question, if the answer was correct, and if it is, you don't have to do anything. But if the answer that you came up with was incorrect, you need to adjust the tree, right? And you do that by asking for what the correct answer was, asking for a question to differentiate that from the incorrect answer, and then replace that answer node that you used for your guess with this little new 3-node tree with a differentiating question, the correct answer on the left, incorrect answer on the right. All right, and then go back and play the game again. But every time that you update the decision tree in memory, you want to write it back out to disk. Okay. Oh yeah, and you begin this whole thing by reading a decision tree in from disk to load it into memory. And yeah, back up your question file before you start, because you'll clobber it a bunch of times usually while you're making this. The initial decision tree comes in from either 20q.txt, or if you specify an argument on the command line, it takes that as the decision tree file. So there's a sample 6-line database, and you can run it like this, which reads from 20q.txt. You can run it like this, which reads from file name. So I recommend breaking this up into some pieces. I recommend having a tree class, having a node class, and having your main PA3 class, right? And at least break it into those 3 pieces, because you do kind of different things in each of those. But, you know, I'm going to let you structure this however you like. I'm not going to put any requirements on it other than, you know, the main class has to be called PA3. So there's some test files available under /temp. This one was given to me by a student many years ago who had a similar assignment at UW and was telling me about it, and gave me the database that they were using. All right, so grading rubric, really straightforward grading. If I can compile your code, 20 points. If it asks questions and makes a guess, another 10 points. If it actually ingests a database file and asks questions according to that, that's another 30 points. So you got 60 points just for basic being able to play the game, right? If I can specify a database on the command line, that's 10. So you got 70 points already for free. 15 for style, that's 85. And then updating the database if it guesses wrong, that's another 15. So don't sweat the points here, right? It's really easy to get a passing grade on this if you start early and you get the core behavior working. But I suggest developing this in steps, right, as always. Suggestion, right? Start off, make a binary tree class, and there's sample code for a search tree on the area linked by Canvas. So you can use that as a bit of a template if you like. But implement a binary tree class and add it whatever you need to support a decision tree. So I recommend your data actually have 2 fields. You have the text itself and then a flag saying whether that's a question or an answer. All right. And then hardwire a tree, right? Pick, you know, some sort of simple tree like that, you know, or that or something, and just cobble together a decision tree. You know, make a node, set the text equal to that, make a node, make a node, make a node, point them to each other in the right way, and just build a tree by hand. It's just pure test code. But, you know, sit down, spend 15 minutes, do that once, so you've got, you know, a tree with a few levels, and now, you know, you just call that code, it makes a tree. You can use that to develop the next parts of PA3. So once you've got a sample tree in memory, work on a method for playing the game. Right? So something that starts at the root, asks the question, moves down, gets to an answer node, tells you what the answer is. Right? And just work on that. Don't worry about updating. Don't worry about file I/O. Get that part working. That's a big piece of the assignment, right? And then your next big piece is reading in from the file. Okay, and we'll talk about how to do that next. But reading the database file into memory, so building the decision tree. And that's a few lines of code if you do it the way I'm going to describe it. Now, if you don't do it the way I describe it, it can be a lot harder. Okay, but I'll describe a really simple recursive way to read that in. And then you can start, playing with the big 20-question database, the 40,000 line one. And that gets to be good fun, right? And then your last piece is being able to extend the decision tree. So this business of getting to the end and getting a new question. And the only sort of kind of tricky thing there is that, as you're moving through, you need to remember where you came from. So if I get here, can you drive it? And I come down and the answer is a car. Well, that's the wrong answer. The answer was actually a bicycle, right? I need to know that this was the previous node and I came to the left so that I can set this node's yes answer to be the root of this new little tree that I create. So you have to keep, one step back. And since your tree always has, at least one question and two answers, there's no edge cases to worry about there. But it's just something you need to think about how you're going to set that up. And again, if you've got a tree in memory that you're just putting together by hand, you can do this and then, I don't know, just print out the contents of the tree and see if it looks right. Right, so that takes a little bit of finagling, but it's not hard if you get it just right. And then you need to take the tree from memory and write it back out to a file, and that's really easy. That's just a node left-right traversal, just NLR. All right, let me give you a warning. Don't try to understand the database file. Okay, I mean you can obviously try to understand it if you like, but don't worry too much about it. So this file, it starts with a bunch of questions, and then there's an answer, right? Which question does this go to? I have no idea. Probably this one, right? Which question does this go to? Don't know, right? It's really easy for us to write a program that will ingest this and organize it as a decision tree. And once it's organized as a decision tree, we can say, so here's an answer, this was the question, this is the yes answer, this is the no answer. But in the file, these things can be all over the place. The no answer could be right after the yes answer. It could be 1,000 lines further down in the file. So you're going to make yourself a really, really hard time if you try to work with this file directly. In other words, if you want to change this to be a new question, you can't just replace this with a Q and then put the two answers below it. Right? You'd need to reverse engineer this file. Don't do that. Okay? Instead, do all of your work on the decision tree. Guarantee it'll save you a lot of effort. So do all your work on the tree in memory. The only time you work with the file is in the beginning. Ingest the file into memory, and after you update your memory decision tree, write it back out to the file. Is that clear? So read in the beginning, do your game playing. If you have to make a change, make your change in memory, and then dump it out. All right, so writing the tree to a file, just do a node left-right traversal of the tree. How can we dump the output database file if we don't understand it? Once you have your tree in memory, do an NLR traversal and just write that into the file. Overwrite the entire contents of the file, and you'll end up with a file in the same structure as what we started with. Yeah, this is a fun assignment, by the way, right? Especially once you start getting some results. It's a fun one to, like, show other people, and people who aren't geeky will still kind of appreciate it. Because, 20 questions. All right, so let's talk about ingesting the file. So you have this file, how do you read it in to create a decision tree? So there's a recursive algorithm that'll work really well. So I'm going to sketch this for you. So let's suppose we open up a scanner, we'll call it S, okay? So construct a scanner for the database file. So that S is the scanner that we can use, next line to read the next line in from the file. And we're going to move through the file, right? But we're going to define this recursive ingest algorithm. All right, so here's pseudocode. So ingest S, build and return a tree by reading from the current location in the file. So we're going to open up the file once before we call ingest. All right, we're going to open the scanner, and then we're going to say something like, tree t equals ingest, or something like that. All right, so what does this ingest method do? Read a line. So when I say read a line, I'm always talking about reading from S. Okay, so read a line. If it's an answer, read next line, which will be the actual answer, right? So this thing is structured as either a Q or an A followed by the actual question or answer. So read the first line. If it's an A, then it's followed by an answer. So read the next line. Save as the data of a node. Set the yes and the no equal to null, and return this node. All right, so read one line. If it's an answer, read the next line, set that to the data field of a node, set the yes and right children to be null, and just return that one node. Okay, and let's say this is returning a tree. Okay, if it's a Q, which is the only other choice, and you can assume the database file is not corrupt. Okay, so if the person specifies a database file, you can assume it exists. You can assume it contains a valid database. So if the line is not an answer, it's got to be a question, right? So if it's a question, read the next line, save that as the data, right, and set your flag if you're using a flag to say this is a question. And now set yes equal to ingest S. So call the ingest method recursively now, and whatever tree that returns, that's what the yes node is. And then call ingest once more, and whatever it returns, that's what the no node is, and then return that node. All right, so that's your whole ingest algorithm. And when you get it just right, it works, and it's beautiful. But it might take a few tries to get it there. So start with, that 6-line file, and the first line that you read will be a question. So let's do this. Here's our 6-line file, okay? And I'm going to mark off where we are in here. So we're about to read this line. So read a line. If it's an answer, well, it's not an answer, so we're going to skip this. So it's a question. Read the next line, which says, is it an animal? Save that as our data. So we're going to make a node which says, you know, question, is it an animal? All right, and then we're going to set the yes node to whatever we get when we call ingest. So we're going to call ingest again. Okay, so we make this recursive call to ingest. It says read a line from the file, so it reads this line. If it's an A, which it is, read the next line. That's a cat. Save that as the data, so we make a node which says answer cat. We set the yes and no children to be null. And we return this node as the value of ingest. So now we come back here where it said yes equals ingest. That makes this point to that node right there. And now it says call ingest again, and we're going to set no equal to that. Okay, so if we call ingest, what does it do? It says read a line. It's an A. If it's an A, read the next line. So we read the word rock. And this says save that as data, so we make a new node, which says we have an answer of rock. It says make the yes and no children null. And then return this node. So the return value from this call to ingest is going to be this node, and our statement says set the no child to be equal to that return value. And then we return this node. So if this was my file that I opened up here and I said t equals ingest, now t is this whole tree. To some degree it'll go down one side at a time, but it does start to bifurcate. And it depends on the structure of this. So if this was a nice, fluffy, well-balanced tree and you wrote the file from it, I think you might be right. But the file will be kind of pathological in some ways. So if you don't see it doing what you expect, don't worry about it. Just see if the final tree that you end up with matches what you thought it should. And if you do this right, when I make this call to ingest and I come back, I should have just read the last line of the file. I should never run out of things. I should never have anything left in the file. So, you know, you usually want to do has next line before you do next line, but technically you don't have to. Technically, when I finish this call, I will be at the end of my file. Now, when I did this call to ingest, right, that only got me down as far as this point in the file. Right, and then when I did this call to ingest, that took me down to the end of the file, and that was when I returned from this original call to ingest. So I was right at EOF. And like I say, you can assume the database file is not corrupt. So technically you don't have to worry about these things, but they're good self-checks along the way. You should end up ingesting exactly the file and nothing more or less. All right, so that's how you read in and how you write out. Just do an NLR traversal. So go through here and go through this tree, and we would write out the root node first, which is question, is it an animal? And then we traverse the left tree, which says answer cat. And then we traverse the right subtree, which says answer rock, and there's your file. All right, that's PA3. So open the database file, either 20q.txt or the file specified on the command line. Pull it into memory. Play the game. If the answer is incorrect at the end, get a new question and a correct answer. Update your tree, write it back out to file. And then go back, play again. You can just keep playing again and again. Questions? So Monday we'll talk about how to write to a file. We're going to use a print writer class, and I think we might have talked a little bit about this already. But basically, we can open a print writer on a file and then just do printwriter.println. And all we ever have to do on this is write, one line at a time. But you do want to stick with this idea of, each line is a Q or an A followed by a colon, and then the next line is either the corresponding question or answer. So when you write it out, you want to stick to that format. Because I will definitely test it with, my own databases, which will look exactly like this. So if you start with... if you start with that and it works, you should be fine. All right. Well, get started on that. Come by office hours on Monday if you have questions about this or about PA2 or anything else. But we'll be going through this for the next few days. We'll go over print writers again. We'll dig into these ingest and game playing algorithms a little further. But that's pretty much what you need to get going on PA3. So then we're going to start looking at class extensions, and that's going to start getting us ready for PA4. PA4, we're going to be making GUIs, and we're going to implement a game of some sort. So that'll be 2 weeks down the road. I'll get PA2 graded and posted sometime this weekend. Other than that, have a great weekend, great rest of the day, and I will see you next week.